So today's lecture is about binary search. The problem with binary search is, given a sorted array, we want to find an element as fast as we can. So in other words, if we can use the properties of the array, the fact that it is sorted, to find something quickly, then that would be very helpful. So we'll talk about how to approach the problem and how to argue about our solution, and finally an analysis of the search complexity. So the idea is that if you're given a sorted array of things, and if you're given boundaries of the array, so in this case I'm going to start with the low being 0 and the high, in this case I'm going to start with 1 above the last element of the array, and soon you will recognize that having high as one element more than the final element in the array to begin with is probably a good idea. So let's say the high is equal to n. So by using some formula, we're going to figure out some middle element in the array, and the middle element must fall between 0 and n minus 1. And this middle element, what we do is we take a target and we compare the, for example, if the target is 5, we compare the target to the a's of middle element if you call the array A. And since target is less than a's of mid, which is 15 in this case, and then we're going to focus on the searching in that part of the array. So it seems like I can continue to apply the same idea to just that part of the array, just focus on the array segment 2, 5, 8, 10 by changing the low and the high. So now the high would become more like mid, and then I will try to compute the mid again and then try to compare the target to the a's of mid, and then continue to do this until I find or not find the element in the array. So one of the advantages of this approach is that if you have an array of size, let's start with an array of size, let's say some power of 2, we can always find, for argument's sake, we can always find a power of 2 that's closer to n. So after one iteration, we have reduced the array size by 2 to 2 to the p minus 1. So our array size is really, our search space is this. And then after another iteration, if you divide it by the original n by n again, you would have reduced the search space by another factor of 2. So maybe we are focusing on this part of the array. And if you keep dividing it, eventually you're going to get to 2 to the p minus p, which is happens to be, if you divide this by p plus 1 times, I guess you're going to get this. So you will have a search array of size 1. So at this point the mid is going to be either the element or it's not going to be, and we can be done after one more iteration. So making the search space smaller makes it easier for us to, you can quickly reduce something from larger to something smaller quickly. So for instance, if you have a million things in an array, and you can reduce them by roughly 20 comparisons, which is happens to be about log 2 of million, and so in about roughly log of n time we can reduce this array to a manageable size. Now, so why are the log algorithms better? So we do know that log algorithms are better because if you assume that your function is some c log n, and even if you double the size of the array to 2, your size of the your logarithm will be 2n, and this would reduce to something of the sort log 2 plus log 2n, which would give us c and c plus the c log n. So even when we double, our log n factor remains pretty similar, and the only thing we are doing is just adding a little bit to make it so it's just a constant factor. It does not depend on the n itself. So it slowly increases. So if you take a log function slowly increase even as n goes to becomes a very large number. In fact, if you can find a log algorithm for something like with billion things, which is roughly equal to about 2 to the power 30 roughly, and you still need, with the log algorithm, you still need about roughly 30 operations. So it gives you a huge advantage in terms of performance when we do log algorithms. So let's talk about the implementation of the this kind of an algorithm that is sort of divide and conquer type algorithm called the binary search. So the first thing we're going to do is we're going to start with the specifications. Our specifications are the same as the linear search, where we require the n to be between 0 and length. We also require that the array to be sorted, which is a precondition. So we have 2 preconditions that are important. And then we have our post condition. So this is our post condition that guarantee that either you're going to find a result whose result is equal to x, that means we found the element x in the array, where the result is within the array boundaries between 0 and n minus 1, or if you didn't find it, then the result must be -1. We must also be able to show that, argue from our algorithm that x could not be in the array A. So in order to begin this, we're going to try to explore the array with lower and upper. So let's say that we start with lower to be the initially lower is equal to 0, and the high is equal to n. That element is not in the array, and the arrays are indexed from 0 to n minus 1. Okay, and so one of the first things we want to do is to make sure that we write a loop invariant to make sure our goal is to go through the array by changing low and high. So for instance, once we compute the mid, it turns out that the x is to the left hand side, then we would make the high equals the mid. Now once we compute it, compare the x to the mid, if it happens to be that x is to the right, we would make low to be mid plus 1. So we are going to make the search space half the size of the previous search array. So the goal is to really change the high and the low within the loop and continue to do this loop until the low is greater than or equal to high. So if low is greater than or equal to high, what that means is that our array size, the length of the array that we are looking at, would be now 0, and hence x could not be in that loop. X could not be in the list. So we write our first loop invariant. So the first loop invariant is going to be that we start with lower to be 0 and upper to be n. Now we like to run the loop as long as lower is greater than the upper, because we said that if the lower is greater than the upper, greater than or equal to the upper, the length would be 0, we would stop it. So the loop invariant, a good loop invariant would be that, looking at the boundaries of lower and upper. So we should be able to prove that the lower is greater than or equal to 0, and we should be able to prove that a good loop invariant would be lower is less than or equal to upper, and we should be able to prove that upper is less than or equal to n. So that's one loop invariant that can be very useful for proving what we want to prove. So we are looking for another loop invariant. So is good, but it's not good enough yet. So we like to have another loop invariant to add to this. So one of the things that I like to do at this point is to really think about how to compute the mid before I get to that second loop invariant. So how do we compute the mid? Now we compute the mid by taking the lower plus upper minus the lower over 2. Now clearly the formula that I write, lower equals lower plus upper minus the lower over 2, is the same as lower plus, from a mathematical sense, it's the lower plus the upper over 2. But the problem is we don't want to use that, since an overflow could result in something like this. So we safely compute the lower mid index. So one of the things we wanted to say is that if you see that the ace of mid is equal to x, then we must return the mid, which would give you a result of this sort here. Now with the current loop invariant, we should be able to prove that if indeed if it returns a mid, then since we know that we can prove the mid is strictly less than the upper and greater than or equal to lower, now try to do that from this formula, we should be able to prove that if indeed the mid was returned as a result, it should be equal to x. You will return from that, as well as the mid that you have is between the lower and the upper, which would allow us to prove this condition here. Since lower is 0 and the upper is n, we can prove the result has to be between 0 and n minus 1. So we can already prove that if it returns correctly, then we will have the correct results. But what we don't have is what happens if the element is not in the list itself. So we're going to continue the discussion about how to develop more loop invariants to prove the post condition, especially if the element is not in the array. So far we have been thinking about something like this. We have low and then we have high. High is not included in the search space, but the low is included in the search space. So we're going to be writing like this. Now if the low is not equal to 0, we can look at low minus 1, and we do know that the following loop invariant. We can just say that if low is not equal to 0, if it's not the first one, then we can look at a of low minus 1. We can be certain that the x is bigger than the a of low minus 1. So a loop invariant you can write is either low is equal to 0 or a's of low minus 1 is strictly less than x. And another loop invariant you can write from the high side is that either high is equal to n, so either high is equal to either n, that means the last element, but if the high is in the middle somewhere, Now we do know that the x must be less than the ace of high. That's why we are still continuing this search. So these are two other useful loop invariants that we can develop and prove to show that this is correct. Now with that in hand, so we have two other loop invariants, and we also prove that this loop invariant can be used to prove one of the post conditions when the result is between 0 and n-1. Now perhaps we can use these two loop invariants to prove the other post condition, that if the result is -1, that means if it's not in the array, then we can indeed prove that it's not in the array. So how do we prove that? So if x is in the list, we already proved the loop invariant implies the loop invariant of first loop invariant we have. This loop invariant implies the post condition. Now if x is not in the list, then we are returning -1. Now what we know if x is not in the list is that we have, if you return -1, we do know that the lower has become greater than or equal to upper. Combine that with the loop invariants imply that lower is equal to the upper. Now since we do know that the ace of lower -1 is less than x is a loop invariant, this implies that since lower is upper, then this implies that a of upper -1 is less than x. Since we also know that the a of upper is greater than x is a loop invariant, we also have this, and a of upper is greater than x. So what we are talking about here is that if given the upper, we are saying that x must be greater than upper -1, strictly greater than upper -1. So it's got to be somewhere here, but the upper is not part of our search space. This one says x is strictly less than upper, so it says that, well, it's got to be here. So so this implies that x cannot be in the list, and therefore it helps us prove this second loop invariant. Now you can leave as an exercise to prove these two things, so you can try to prove that they are indeed loop invariants. Okay, so finally proving the termination. Now our loop condition is while the lower is less than the upper. Now we do know that the lower is always increasing, so the only way lower changes is lower becomes mid plus 1. So lower is an increasing function, and the upper is always decreasing, because the only way upper changes is upper becoming mid. And so since we know that the mid is strictly less than the upper, and the new mid is going to be less than the old upper, and hence upper is a sort of a decreasing value. So eventually that we must have the condition, the termination condition, that lower is greater than or equal to upper, that we can prove the loop termination condition. So now finally, to complete the code, we can write the code for the loop. So our code for the loop is then we have if ace of mid is equal to x, return mid, else if x is less than ace of mid, what we like to do is to make the upper to be the mid, and else we would make the lower to be the mid plus 1. Now using these two conditions we have here, you should be able to prove the two loop invariants. And so this concludes the lecture on binary search.